In this second video on standard derivatives, we consider the trigonometric functions. We only look at the derivation of the derivative of the sine, as the same story works for the cosine. Let us first just graph the sine function. Remember that in calculus we calculate our trigonometric functions using radians. Thus the maximum of the sine occurs at pi over 2. What would the derivative of the sine look like? Well, the sine starts off going up, so the derivative is positive. Subsequently, the derivative is getting smaller and smaller until it passes the x-axis at pi over 2, where the sine has a maximum. Then the derivative is negative as the sine is decreasing, with its lowest value at pi, where the derivative is mostly going down. Then it goes up again as the sine is curving upwards and passes the x-axis again at 3 pi over 2, where the sine has a minimum. Then it increases again until 2 pi, and subsequently we see that because the sine function is 2 pi periodic, the derivative also repeats itself. We have now drawn the graph of the derivative. Does it look like a function we know? Indeed, it looks like the cosine. Notice that we can easily remember it is plus cosine, as the derivative must be positive at x equals 0, since the sine is going up. Let us now consider this more precisely. As we know, the sine is the y-coordinate of the point on the unit circle for an angle phi. So we need to know what happens to this y-coordinate if we slightly increase the angle from phi to phi plus delta phi. To better see the change in y-coordinate, we add a little triangle over this little arc. This is a very small triangle, so let us zoom in. Now, we know two things. Because the arc is so small, the circle looks like a straight line in this zoomed-in picture. Just like the surface of the Earth appears flat for us, even though it's a big sphere. Recall that the length over an arc of the unit circle equals the associated angle in radians by definition. So the length over this arc equals delta phi. It is, moreover, approximately the same as the length over a straight line with the same endpoints. This straight line is the hypotenuse of a right-angled triangle, one of whose sides is a change in y-coordinate. The change in y-coordinate can then be expressed as the length of the hypotenuse times the cosine of alpha, which approximately equals delta phi times cosine of alpha. It remains to find the angle alpha at A, which is the angle between a vertical line and the tangent line to the circle. Let us zoom out again to determine alpha. Note that the tangent line to the circle is always orthogonal to the line from the origin. Moreover, the angle below A equals pi over 2 minus phi, so the angle alpha equals pi minus pi over 2 minus pi over 2 minus phi equals phi. We conclude that the change in y-coordinate equals approximately delta phi cos phi. Plugging this in the definition of the derivative, we find that the derivative of the sine equals the limit of delta phi cos phi over delta phi, or the cosine of phi.